Jeff's and the Center for Space Medicine, Nancy Gibbons, and everyone's support, because when I joined Baylor in 2008, I had no idea about space medicine. I did not know that there was a Center for Space Medicine at Baylor that one could get involved in, and I had no training in space medicine at all. I was trained in neurology and then did vascular neurology and neurocritical care, and so for the first years of my early career, that's what I did. I went to the neuro ICU, took care of stroke patients, patients with elevated intracranial pressure, and I became interested in the physiology of how everything is working together, and then also how the brain and the rest of the body are interacting. And so based on that, my interest in that, I just immersed myself in trying to learn everything I could about the physiology of intracranial pressure. And I realized that there's not that much to learn about it once you get into it. And there's not that many people that are interested in physiology. Most people that go into medicine, they might be interested in a specific disease, and then they do research in one thing. And maybe because I have a little bit of attention deficit disorder that's undiagnosed, I kind of wanted to learn everything. And so physiology was something that I felt like it was interesting, that you could apply to a lot of different areas. And then fortuitously, the VIP syndrome, the visual impairment, which is now SANS, came around. And that was about 2011. Through some connection, I was invited to the VIP conference. And then the night before, they asked me to prepare a presentation about brain physiology. So I pulled out an old lecture that I gave to the fellows, residents, and I basically gave that lecture, and then they apparently liked it enough to invite me back to other conferences. And then there I met some people from the Center for Space Medicine, and then Jeff Sutton as well, and started networking and trying to, at that point in my career, I had not committed to any specific research area. I had done some coagulopathy research, but I thought that the space research was a lot more interesting, so I started doing some small pilot studies that were unfunded in my spare time when I was off service. And then I had attended the IRB and became an IRB member, and so I was able to write protocols. And so I kind of just did it myself with the help of the Center for Space Medicine and other people that I knew that were more experienced at the time, and sort of gradually built my research career that way. Applied for some funding. I did not get funded at first, and so that was disappointing. And then I applied again later on. I got some directed funding, and then after that I was able to get competitive funding from the National Space Biomedical Research Institute, NASA. And so now it was kind of a gradual process, but I encourage all of you to keep your mind open when you're looking for what you want to do with your career, and don't just think that if you do one specific area that you're limited to that area. You can pretty much, with enough motivation and connections, you can do other things. So today I'm going to be talking about a really fascinating area that is related to the effects of microgravity on the brain and the eye, and how can we learn about that using ground-based analogs, because we don't have that much real estate for research in space. It relies on the International Space Station, and so that's a great platform, but there's a lot of competition, so we have to look at other venues to try to simulate the microgravity-based effects. Okay. So I'm going to talk mainly about the SANS syndrome, which is Spaceflight Associated Neuroocular Syndrome, which, as you heard in the last lecture, is the most pressing problem as we're considering a mission to Mars, because we really don't know what happens after about a year. Does the brain suffer permanent brain damage? Is the eye going to have permanent structural changes and lead to impairment in vision for the rest of the astronaut's life? We just don't know. And how can we study this using a bed rest analog to study the cerebrovascular and ocular symptoms? Are you all familiar with bed rest studies? So the patient, healthy subject, they go in a bed, and they're usually at 6-degree head down tilt for up to, the longest I believe is about 70 days. We're going to be doing a study for 60 continuous days. They're stuck in the bed, They have to use the bathroom in the bed, eat all their meals, exercise if they're allowed to. They're not allowed to lift their head off the bed at all. Like a continuous, their head is stuck on the bed for 60 days. Then the reason we're doing this is to try to see if we can understand, does anyone want to volunteer? They'll pay you 16,000 euros if you want to volunteer, but you have to probably learn some German. Okay, so what is happening that this is so important? It's that there's this constellation of symptoms. There's impairment in near vision. So that's one of the first manifestations is that astronauts, they're trying to read something and they're just having trouble focusing, but they're able to see in far distance. So they're having an acquired hyperopia. So they did not have this before, and then it's developing on the ISS after some period of time, a few months, and it's correctable by space adaptation lenses. So they can add some diopters and then they can see near vision. Why is that happening? We think it's because the back of their eye, their choroid, is becoming engorged with extra fluid, and that's maybe shifting the focal point of the light on the retina. So it seems to be specifically pushing the back of the eye forward. What's behind the eye? You have cerebrospinal fluid in the optic nerve sheath that is connected to the brain. And so if you have elevated intracranial pressure, then that cerebrospinal fluid is going to then look for a pathway to drain out of the skull. And one of the pathways is the optic nerve sheath, which is a tunnel connects to the back of the eye. And so it's going to push on the back of the eye. And then also the blood from the choroid, it's venous blood, maybe also not draining well. And so that venous blood's also going to back up. And that choroid drains into the internal jugular veins, which also may be backing up with fluid. So there may be multiple extra resistive forces that are preventing cerebrospinal fluid and blood from escaping the skull. And it's manifesting with the optic disc edema that you can see there, which Dr. Norris could show there. Here's pre and post. We see that when intracranial pressure is chronically elevated. That's usually the main time we see that. And the lumbar punctures have been moderately elevated after flight. We don't know what they are in flight. There is some evidence that they may be actually lower than the supine position on Earth, but higher than the upright position. And so since we spend 2/3 of our day in the upright, either sitting or standing, then the pressures may be on average higher in microgravity. But there may be more than just pressures, and maybe other factors related to the weightlessness. This is just showing on the expeditions 1 through 48. 40 astronauts have had one or more of these findings. This is how these are tested and these are affected. And so you have 10 with disc edema, optic nerve sheath distension 14 out of 47, tortuosity of the optic nerve sheath, some cotton wool spots, which we don't, these are kind of maybe unrelated, but we see these in hypertension. Thickening of the retinal nerve fiber layer, so it's probably thickened because of fluid, because it seems to be somewhat reversible. And there's choroidal folds here. Globe flattening, that's the phenomenon where the posterior globe seems to be flattened a little bit anteriorly. And refractive error shift, that's that hyperopic shift that we were talking about. Okay, what do we know about in space, what's happening to our brain and eye? Well, it's important to understand the concept of hydrostatic pressure gradients, because that is probably the primary issue that's affecting the physiology in the body. And so pre-flight with normal Earth gravity, you have this gradient of pressure from your head to your toe. And so this is based on the column of weight. So 200 millimeters of mercury, 70. So your feet, like at the end of the day, or you're sitting for a long time in the airplane, you notice your legs or feet are a little bit puffy. Or when you wake up in the morning, you have the opposite effect where your face is puffy, because your fluids are moving back and forth across the lung axis of your body depending on gravity. So it's important, so in microgravity, you don't have hydrostatic pressure because there's weightlessness. So your body, all the body tissues are unloaded, and so everything in all the different directions there's no hydrostatic pressure in your body. There's still pressure in your body because otherwise you wouldn't have circulation of blood. Your heart's pumping, it's generating pressure inside the vessels, and you have compartments which have a pressure, but there's no hydrostatic pressure element to the pressure, the internal generated pressures. And so that changes the transmural pressures on different blood vessels and different compartments in the body. So then there's these bed rest models. You can lie flat. So you would think, so does the horizontal equal microgravity? No, why not? It looks like you have 100 everywhere. What's the difference? What's that? Right. Well, so okay. There's the g. There's 3 different vectors to gravity. There's gz, which is the long axis. There's gy, which is the across the chest, and then there's gx, which is from anterior to posterior. And so you still have a gx component. You neutralize the gz component, but you're still having weight going from your chest to your back. And so what that means is that your blood vessels in your chest are still having pressure in that direction, whereas in microgravity they're not. So the chest diameter is your chest wall expands in microgravity, and so that's why your central venous pressure drops in microgravity, because you have more, your compartment's bigger. So when you have a bigger compartment in the same volume, you drop your pressure. If you remember that from like physical chemistry and undergraduate. So the size of the compartment plus the volume equals that's compliance. So that's how you can determine the volume pressure curve. So there's still effects that are not like, so if you want to study, so then 6-degree head down tilt bed rest, there's a slight fluid shifting toward your head due to the difference in pressure gradients there. And so this is what's traditionally used. 6-degree head down tilt, there's nothing magical about 6-degree head down tilt. If somebody's 10 feet tall, then they're going to have more hydrostatic pressure than if they're 3 feet tall. So the height may be one factor that affects, it's not just, so you could maybe consider adjustable head down tilt angles. But this is the standard one. It's just for convenience that we use 6-degree head down tilt. And it was based, from what I was reading, on a subjective experiment where the cosmonauts felt like they were in space after they came back from space, and they put them on a bed and tilted them to 6-degree head down tilt. They said, now I feel like I'm back in space. And so then based on that, I think that was that was the anecdote that I was reading about. Headward fluid shifting, so it's very visible. Here's a pre-flight and in-flight. You can see one of the scalp veins is very prominent there, and there's less wrinkles as well. So you have this may be an indication that the venous blood is not draining properly. These are the choroidal folds that are seen post-flight, which are little ripples in the choroid layer of the eye. It's unclear exactly what the etiology may be due to some rapid fluid changes. And then here you can also see the choroidal folds. This is the macula. Okay. And then here's a normal globe and optic nerve sheath. And here's the cerebral spinal fluid. This is the optic nerve. And then this is in one of the astronauts. You get this bulbous appearing dilation of the optic nerve sheath and a flattening of the posterior globe. to understand what may happen in microgravity, it's important to realize that our intracranial space has compensatory mechanisms that allow us to have some extra volume before the pressure goes up. So here's a normal state. We have the brain, we have the arterial blood, the venous blood, and the cerebral spinal fluid. So what happens if you have an expanding intracranial mass? So what will happen is that you'll shift some cerebral spinal fluid into the lumbar subarachnoid space, and you'll also compress the dural venous sinuses, and you'll decrease your venous volume. And then, but the mass will keep expanding, and then eventually you're going to reach the limits of your compensation for that extra volume, and then the pressure is going to go up. The pressure goes up, you're going to have shifting of brain structures, brain herniation. And actually there is some, so I didn't include this for the sake of time, but there was an MRI study done by Roberts et al., published in the New England Journal of Medicine, looking to see what happens to the brain after spaceflight. And it actually shifts upward toward the vertex, and you get compression of the dural venous sinus. So the brain appears to compress some of the venous outflow pathways of the brain. It's not a whopping effect. It's a little bit subtle, but it is there consistently. And so it does seem like there are definite brain structural changes. And the lateral ventricles increased the amount of cerebral spinal fluid as well, which may be secondary to the venous outflow obstruction that's happening. This is the volume pressure curve that I was talking about. Normally, let's say we have a normal intracranial space, and then you add some volume, the pressure won't change much. But then once you reach a critical state, small changes in the intracranial volume will increase the pressure by a much higher amount. And so that's where you have the low compliance or high elastance of the system. It's also important to realize that our cerebral blood flow is very tightly regulated and related to carbon dioxide levels. And so this is another issue on the ISS, is that the carbon dioxide levels, the astronauts are always breathing carbon, they're always exhaling carbon dioxide, and they have to manually clear the carbon dioxide from the space station because they're stuck with the ventilation that's there, and they don't have the natural plants and trees that are absorbing the CO2. So they have to use artificial measures to lower the carbon dioxide levels. And so this may be affecting the cerebral blood flow regulation. There may be pockets of CO2, so that in some areas there may be spikes in the CO2 levels, which may then affect the cerebral blood flow. And so that's another element that might contribute to extra volume inside the skull. So if you're if you have a hose and you turn on the water, what happens, the water is going to accumulate, and then eventually it's going to drain out. So like a bucket, and the water goes up, and if there's holes in the bucket, the water's going to drain out, and then you'll get back to a certain level, but that might take some time. So in the meantime, what's happening to your intracranial pressure, and what's happening to your cerebral spinal fluid pressure, and then what's happening to the back of your eye, because all of those things are interlinked. And so you might get a transient pressure in the back of the eye that may be causing some strain over time and then leading to some of these structural changes. The cerebral autoregulation is another factor where we try to maintain a good cerebral blood flow despite a range of cerebral perfusion pressures. And this is also affected by carbon dioxide. So this might be also affecting your cerebral blood flow. And then once you have the arterial blood in, it has to come out. And it usually comes out via the internal jugular veins. But there's also an important pathway, which is the vertebral venous plexus, which is more active when we're in the standing or upright position. So on Earth, more of our blood flow actually drains on average from our vertebral venous plexus. And only when we're sleeping or in a head down tilt position, then the internal jugular veins are the more important route. But in space flight, it's the internal jugular veins are always having to be active to drain the blood. So here's just an example, supine. Here's the internal jugular veins, and here they are upright, so you can hardly see them. So here, and you don't really see them well, but look what happens to the vertebral venous plexus compared to before and after. And then the CSF has to drain through pathways, including the dural venous sinuses, but then also along the cranial nerves, like the olfactory nerve, so our sense of smell may be related to CSF drainage, and also the optic nerve and other lymphatic and spinal subarachnoid villi. So what are the tools that are available on the International Space Station? There's limited space. They're limited by the mass of how much they can launch up there. And so they also want to avoid radiation. So what you can use are ultrasound and other low energy electromagnetic radiation. You can take pictures with a fundoscope. And so this is one way that they're able to detect as it develops what is happening with the optic disc edema. They have OCT machines, so that's one of the more high-tech devices, and they're going to upgrade that with the next version as well. And ocular ultrasound, which gives you some idea of the optic nerve sheath diameter and posterior globe flattening. Some of these methods are operator dependent, and so you have to have somebody monitoring on the ground in order to see if they're doing it the right way. Internal jugular vein ultrasound, which is something that I think is important because the cross-sectional area of the internal jugular vein may be an indication of the fluid status of drainage from the brain as well. So that's the main outflow pathway in the microgravity condition. We know that elevated carbon dioxide can cause drowsiness, headaches, increase the cerebral blood flow. And so this is 1%. It may not sound like a lot, but this is enough to cause a substantial increase in your cerebral blood flow. And the levels on the ISS are on average 0.5%, but they've been reported to go up to 1% before. So they're 10 to 20-fold higher on the space station than Earth. And CO2, as I showed you before, is a potent vasodilator and increases cerebral blood flow. And so we think that there could be, at times, up to 20% higher blood flow to the brain in microgravity. And there's even a classification by the International Society for Headache Disorders that includes a space headache as a diagnosis. Just to keep in mind, in case you see an astronaut having a headache, then you can maybe diagnose them. What happens to the cerebral blood flow velocities in space? Well, it's been measured, actually, with transcranial Doppler. Transcranial Doppler ultrasound is a type of ultrasound that we do in the ICU. You can do it in the outpatient setting. It uses a 2 megahertz insination of the large arteries, like the middle cerebral artery. And it's thought to correlate with your cerebral blood flow, but it's looking at velocity rather than flow. So it may be dependent on, so the diameter, if it's not stable, may give you a false reading. But in general, you can look at trends. So what's happening is here's some different astronauts, and here's pre-flight, 1 week in space, 2 weeks in space. You see on average that there's not much of a change. In fact, there's a little bit of a decrease followed by an increase. But what's happening here, there are two. This is why it's important to plot the data individually when you have a small sample size, is that there's a few astronauts there that seem to have an increase in their blood flow velocity that increases with time. And this may be because some people are more sensitive to the physiological effects of spaceflight, like the carbon dioxide. Now, looking at the ground-based analogs that are used to simulate spaceflight, there's a number of different analogs. A lot of these are looking at the behavioral effects, because we don't want people to go crazy when they're in a small capsule to Mars. So it's important to know, the logistics and dynamics of putting people in a closed environment. I'm not going to be talking about those, and there's a space radiation lab. Radiation, it does probably affect the brain in certain ways that we're not aware of. It's hard to test, it's hard to find people that you can irradiate in a ground-based analog, so they're usually using animal models. So I'm not going to talk about that one. But there's parabolic flight, so I'm going to briefly show a study that was done with parabolic flight, and then I'm mainly going to be talking about this number 4, which is NVHAB, which is environmental habitat, which is in Germany at the German Aerospace Center, where our group's done a lot of work there over the last few years to try to figure out if that's a viable ground-based analog for spaceflight. And we were skeptical at first, but it turns out that it may be a useful analog after all. So here's parabolic flight, and they also call it the vomit comet because it makes some people really sick, because it's like a roller coaster that you're just basically going in a bunch of, like a sinusoidal pattern back and forth for like 20 to 30 parabolas. But then when you reach this point here, you are in the microgravity for 20 seconds. So you have 20 seconds to study microgravity. So you have to be very quick, and if you're doing a continuous measurement, you might be able to get some idea of the effects of microgravity on the physiological systems. But it's, as you can see, it's followed before and after. There's hypergravity before and after. And so we don't really know what to make of parabolic flight because of it's like a very short, rapid fluctuation between hypergravity and zero gravity. But it is useful for looking for things that you expect are going to reach their steady state quickly. And this is a study by Lawley and Ben Levine, where they were able to find people with Ommaya reservoirs that were cured from their malignancy, and they instrumented them with a butterfly needle hooked up to an ICU type monitor, and were able to do a continuous monitoring of the intracranial pressure and the central venous pressure as well during a parabolic flight. And what they found, interestingly, was they saw here, here's gravity, so down here is 0, and up here is 1.8. And so look what happens when the gravity is 0, their central venous pressure drops, and their intracranial pressure is dropping. But it's still elevated at 15, which compared to the upright position where it's close to 0 is a lot higher. So yes, our intracranial pressure right now is 0 or negative a little bit when you're sitting. So it's still higher, but it's not as high as the supine position, which in their study was approximately 17, 18. So the conclusion of their study was that the intracranial pressure is lower than the supine position on Earth, but on average it's higher than the Earth-based level since we spend 2/3 of our time in the upright position. I kind of mentioned about the ground-based analog. Pay attention, this is on the quiz at the end. So you have the GZ is the head-to-toe vector. Here's the GY, and the GX is going through the chest. And so the bed rest analogs, they do not get rid of that vector. They do get rid of this vector, make it neutralized. And this would be the same. Okay, so this is from a review from Alan Harkins, who's done a lot of work on this. And here's the upright position. So 10% of our body weight when we're upright is in our head, and 100%, we feel 100% of our body weight in our feet, and 50% if you split the body in half at this level. So the farther down you are, then the more weight you're going to feel there. In bed rest, you have still, this is just illustrating that GX is still there. It does not go away. Microgravity is the only situation where you can eliminate all of the hydrostatic pressure gradients. Now, what do we know about the effects on the eye of bed rest studies? This was from Taby et al. They did a 14 versus 70 days of head-down tilt bed rest with a normal atmosphere. And they saw that the intraocular pressures increased initially, but then toward the end of the 2-week period, approached the baseline. And so this may be due to some of the adaptation that happens with our body fluids after we're head down tilt. Then we get a diuresis because if we have fluid shifts toward our chest and our aortic baroreceptors and our carotid baroreceptors are active, then they sense too much volume, and so then our kidneys are made aware of that, and we get rid of some of the fluid in the body. After 70 days, you see kind of a similar initial trend, and then it normalizes after that time. What happens to the retinal nerve fiber layer? Interestingly, it starts to increase after 14 days. This is the pre to post change in retinal thickness. It increases by about 4 to 5 micrometers, so it's not a whopping amount. By 70 days, it increases by 10 micrometers. And the retest accuracy of OCT, optical coherence tomography, is so high that that's a very significant change. Here's just a visual example of this. Here's a pre and post at the level of the optic nerve. And so most of the changes were at the optic nerve level. And this is consistent with what we're seeing in the astronauts, that the optic nerve is getting pushed anteriorly. So it does seem that the bed rest is producing some of the same structural changes that are happening in the bed rest. Then they looked further at whether exercise as a countermeasure would affect that. And they didn't see much of a difference there, but what they also found the same 7 to 10 micrometer increase in the peripapillary, so around the optic nerve thickness. They did not see any changes in optic disc edema, though, in that study. So to that point, it was not looking that promising for bed rest as an analog to reproduce the optic disc edema. And there had been no other analog in a healthy person to simulate that until, well, so I'm going to get there. But before we get there, we had a groundbreaking study that the Center for Space Medicine and the NSBRI supported, where our big team of investigators, I was the PI along with Dr. Dorit Donneville. We assembled investigators we collaborated with the DLR. So we didn't just come in there and say, we want to use your facility, just conduct our study for us. We actually stayed there for the whole study, and we made them scientific collaborators. And so by doing that, everyone was enthusiastic about seeing the study successful. And we also, for the first time, we had a double-blinded study with carbon dioxide in the atmosphere. So we had, it was a small pilot study with 6 healthy subjects. They each had 2 different campaigns. They were randomized to either 12-degree head-down tilt plus 0.5% CO2 versus 12-degree head-down tilt in regular air. And they had a 1-week washout period, and they repeated the same measures like MRI, OCT, and everything before and after. The main purpose was to determine whether this facility was worthy of other studies, because NASA was really interested in seeing whether they should do further studies there, because before then there were only small internal pilot studies. So we were the first American investigators to actually go there and do any kind of bed rest study. And so here's the facility. It's very cutting edge. The German government spent a lot of money on that. And it's Here's an example of the head down. These are the rooms that we actually used. And we had different areas we made it like an assembly line where we had different technologies. And the subjects would come in, we would hook up probes to their head. We would do like near-infrared spectroscopy, transcranial Doppler, non-invasive ICP. We also checked their arterial blood gases and did a huge number of measurements to see what was going on. Here's the non-invasive intracranial pressure monitor. It's not ready for prime time yet. And in fact, there's another device that the company transferred to the US, and now they want me to test their newest device. And so it still doesn't, it's not quite working yet, but hopefully this next version. We did near-infrared spectroscopy, cognitive testing. Here's the MRI. So we kept them in the head down tilt position during the MRI scan as well. And so I'm not going to go into all of our findings, but we found some interesting findings. We published 5 articles related to the effects of the short-term head-down tilt with CO2. We found that the CO2 actually improved cognition a little bit in some of the measures, so maybe the increased blood flow was good for them. But the head-down tilt was bad. It decreased cerebral blood flow. So there's there's opposing effects of head-down tilt versus the CO2. They may be counteracting each other in certain aspects. The study wasn't long enough for us to see changes in the eye. It was only 28 hours of continuous 12. It was a steeper angle than the 6 degree. So, but the preliminary indications are that it was successful to use CO2 and head down tilt, and it paved the way for a 30-day study, which was done. This was called the Vapor study. I was not involved in this study. This was a very interesting study by Steve Laurie et al. They did 30 days of head down tilt plus CO2 at 0.5%. On a side note, 0.5% CO2 is the maximum allowable CO2 level that you can give in Germany for occupational health standards for the operators. And so when we were there for the SpaceCOT study, we initially wanted to do 1%, but they wouldn't let us. It would have been, we would have had to wear masks that would filter out the CO2, and it would have been very tedious. And so we ended up compromising and saying, let's do 0.5%, which happened to be the average level on the ISS anyway. So it ended up working out well. And that's the level they used for this study, where they had, in this study, they had more subjects, and they also had women in the study as well. 6%, because that's the traditional level. The 12% would probably not be tolerable for 30 days. So our subjects were sliding down the bed. We had to like put a certain material to keep them in place so they wouldn't slide down and hit their head on the edge of the bed. The other thing that, based on our study, that they realized was important was not using a pillow. And that, because there's evidence that when you increase your head, even with a pillow, the ICP will drop sufficiently enough that might reduce the effects of the head down tilt model on the cerebrovascular system. So this was the first time that they ever had that for 30 days with no pillow. And they were also stricter in terms of monitoring them with video to make sure they weren't cheating and getting out of the bed. So they had to stay in that position. And then, so during the study, they found they were doing their periodic OCT checks, and the ophthalmologist noticed that there was optic disc edema developing. And so they added on a fundoscopic evaluation in the selected subjects that were developing the changes on the OCT. And this is the example. It's hard to kind of tell, but these are 2 different subjects, and they had a halo. So one of them had grade 2, which was a circumferential halo of edema around the optic disc, and the other one had a C-shaped halo with a temporal gap, which indicates a freeze in grade 1. So those are both abnormal. they also had increased thickness of the retinal fiber layers as well, and total retinal thickness. So this is a summary of those bed rest studies. So this one was that 14-day and the 70-day by Taby et al., which was 6-degree head down tilt with no CO2. This one's the 30-day with CO2 and the strict head position. So those are the two factors that are different, but we don't know now because there was no CO2. These other ones, and also they were allowed to be more liberal with getting out of the bed and like lifting their head up, going on their elbows. So we don't know which of those two factors, because in the NASA study, they did not have a non-CO2 control group. Everybody was in one arm. So if you're designing an experiment, then make sure you have a control group. Otherwise, you're going to finish your study and have to do another study. And so luckily, and then what about countermeasures? So this kind of paves the way for the next study, which is we've determined that head down tilt does produce some of the changes in the SAND syndrome, but what about a countermeasure that would be practical? Is this practical, going to Mars? It may not be. What about a centrifuge? So that's the thought, is that maybe you can do a centrifugation like you've seen in sci-fi movies to try to restore the gradient, hydrostatic pressure gradients. We probably can't design a whole space station yet that's a centrifuge, but we can do a short arm centrifuge on the space station that may be useful, that you can spin the person, and if their head is toward the center and their feet are out and you spin them, then their fluids will shift toward their feet. So depending on how fast you're spinning them, you can alter the gravitational vectors. So a few weeks ago, we went over there for the dry run for the centrifuge. So we have John Clark and Karina Marshall-Goebel. She was one of my collaborators, and we had the German engineers there and on the study team, and we set up some of the devices that we're going to be using. So here's a transcranial Doppler and also a NIR, so we were able to do multiple monitors at the same time. So we looked for efficiencies in the experimental setup, and then we actually ran the centrifuge to get some idea. And no one's ever seen this except for our study team. We're going to be presenting it at the NASA HRP meeting. So you're privileged that don't tell anyone what we found. But one of the tests that we did, which nobody's ever done before, is we did an internal jugular vein ultrasound continuously on the centrifuge. So initially the idea was they had a robotic probe built into the centrifuge, but as soon as we arrived there, they said, "We have bad news for you. We can't use the robotic probe. We tried it before, and we couldn't find the internal jugular vein, and it caused them to pass out." And we didn't know what they were doing, because the internal jugular vein is the world's easiest vein to find. It's especially if they're supine. So I'm not sure what they were doing, but the robotic probe, they just wouldn't let us touch the robotic probe. So I said, why don't we just use a portable ultrasound machine and have the subject hold it on their clavicle? And they're like, "Oh no, that's too difficult. It's very difficult to find the internal jugular vein." I'm like, "I'm not sure what vein you were looking for, but the internal jugular vein is very easy. We'll show you." So we got the portable machine, and sure enough, the internal jugular vein was very easy to find. And we said, "Okay, rest it on your clavicle lightly." And so we trained the person. He was very excited. And so it ended up working. And so now we're going to include it into the study. And so this is the internal jugular. Here's the carotid. So it's easy to separate those. And then here's the subject that we're able to monitor. And so I have a video that hopefully this will, let's see. So, okay. So we spun, there's the subject spinning around. So they're going to be doing this in the study every day for 60 days for 30 minutes a day. So there's 24 subjects, and 16 of them are going to be spun every day for 30 minutes. Of those 16, 8 get a continuous spin, and the other 8 get 30 minutes, but it's like 5 minutes on, rest for 5 minutes, so it's like on and off, like every 5 minutes, but it's still 30 minutes. And with the idea that will that offload the cerebrovascular and ocular effects of the head down to 6-degree head down tilt. So here's the preliminary data from that subject from the study. We did this is a NIRS by Gary Strangman, who's also supported by Center for Space Medicine and the NSBRI that I collaborate with. He developed a NIRS that, this is really interesting. There's 4 different NIRS probes that we put, one on the head. So this is the forehead, chest, the thigh, and then the calf. And we did this continuous to see what happens to the blood volume in these compartments when we spin them. And then there's shallow and deep, so you can know that because the NIRS looks at, it has different depths. And so the head, here's the supine baseline. Then this is as the centrifuge is ramping up. And then when it reaches 2G at the feet, because there's 0 at the head and 2 at the feet. So what you see is that the head, so the volume decreased. And then afterwards, there was hyperemia. You see that? The chest also increased, but the thigh actually went in the opposite direction. So these 2 decreased, and these increased as we spun them because the blood was shifting toward their feet. So it made perfect sense for what we were expecting. And at the calf, you had the most blood volume when you spun them. So this is one way. So now we know physiologically that the countermeasure is probably going to be doing something. And then this is the video. I took a video of the internal jugular vein. And we're going to present this hopefully at the NASA meeting. So this is baseline. And you can see this is the carotid, it's pulsating. And here's the internal jugular vein, which is bigger than the carotid. You can demonstrate that that's the vein because you compress it and you see it's easily compressible. So there's no movement so far. And then okay, now look, okay. You see now that there's spinning. It's kind of ramping up. Now just watch closely what happens to your internal jugular vein. So they're freezing it, obviously, and taking some snapshots as well. But what you can see is as you get up to that targeted G level, the internal jugular veins are basically collapsing, which is what we expect when we're going from a supine to an upright posture. Same thing happens to us. If you don't believe me, go into the hospital bed, get a sonocyte, and start from supine, and then put the bed up. And when you reach about 45 degrees or higher, you'll see your internal jugular vein will just close up. And so we saw that, and it persisted through the, I'm not going to go through, but here, look at it now. It's completely closed. And then, let me just go to the end. Okay. So now look what happens when you stop the centrifuge. It immediately opens back up, and you almost get like a hyperemia. And so You see how big that went in a very short time. So there's a very rapid dynamic change in your blood volume that we saw. But this is just one person, but based on the NIRS and the internal jugular vein. So for the Space Sense study, which is the name of the sub-study of the AG Breeza study, which is this artificial gravity bed rest, we're going to be including those plus a bunch of other measures, including MRI, and seeing what happens in that model. So in conclusion, we think that head-down tilt bed rest is a reasonable analog for some of the headward fluid shifting in microgravity. Given the limitations, though, that we have to keep in mind, such as the preservation of the GX vector, therefore tissue weight does remain. Some of the findings of SANS have been simulated now, like the retinal nerve fiber layer thickness and optic disc edema. It'll be necessary to determine the importance of CO2. And so in our study, NASA is really interested in our control group of the 8 subjects that are not getting artificial gravity, because then they'll have the head down tilt with 6 degree without the CO2, which they can compare to the vapor study, which included the 6 degree plus the CO2, and differentiate what are the effects of the CO2 versus the regular ambient atmosphere. And then we'll have to see whether this artificial gravity countermeasure counteracts some of those effects, which would be useful when we're going to Mars to have some non-pharmacological countermeasure. Now let's see if you were paying attention. Which of the following features of spaceflight-associated neuroocular syndrome is most likely to cause functional impairment? Is it the optic disc edema, the hyperopic shifting, choroidal folds, optic nerve sheath tortuosity, or the cotton wool spots? This may be a trick question because I know that Dr. Norsk had said something, but if you think about it, you should get the right answer. So who thinks it's A? Okay. Who thinks it's B? Okay, B is the correct answer because it's the hyperoptic shifting which is causing the functional disturbances in your vision. All of these other things may or may not affect. So the choroidal folds may be underlying the hyperoptic shifting, but choroidal folds may not themselves produce, it's not definite that they would produce any findings. Okay, so which of the following vectors is affected by head-down tilts mainly? Is it the GX, the GY, the GZ, all of them, or none of them? Is it GZ? Right, so it's the GZ that you're mainly affecting. And which of the following body positions is typically used for head-down tilt? So 6 degree head down, so -6, yeah. And which of the following veins is the main cerebral venous pathway, outflow pathway in the head down tilt position? Correct, okay. What body position produces the highest GZ hydrostatic pressure gradient at the feet? So standing. So when you're sitting, you're actually, part of your body is not having weight, the hydrostatic weight, so it's actually standing is worse than sitting. So thanks for your attention. Hope you learned something. Have you read this article about standing desks? So standing desks are like the new rage. And it turns out that there's evidence that they may be more harmful than actually sitting. So I was reading that article and I was thinking, well, that could be true because if you're standing, you have more hydrostatic pressure at your feet and your cardiovascular system may actually be more stressed out than if you're just sitting. And so the conclusion of the article is that instead of just standing, you should be doing exercise as well and not standing at your desk. So don't invest in standing desks. You're going to lose your money. Sure. Thanks. Okay. Cool. Thanks. Thanks. Yeah, that's pretty fascinating stuff.